Hello, this is problem number 1 in homework 5. This talks about the acceleration due to gravity on Jupiter relative to the acceleration of gravity on Earth. We know that g in general is given in terms of the gravitational constant, universal gravitational constant g, mass of the planet over the radius of the planet square. If we say using this, if we can write a ratio, so that will be acceleration due to gravity on Earth would be g times mass of Earth over the radius of square. And similarly, gravitational acceleration due to gravity on Jupiter would be the same universal constant, mass times mass of Jupiter over radius of Jupiter square. If we divide the two equations, we get acceleration due to gravity on Earth over acceleration due to gravity on Jupiter is equal to g cancels out mass of Earth over mass of Jupiter times radius of Jupiter goes in the numerator because it's the ratio of inverse quantities pretty much swap their positions. So radius of Jupiter over radius of Earth square. We are given that the acceleration of gravity on Jupiter is 2.5 times, 2.4 times acceleration due to gravity on Earth. So we have 1 over 2.4 is equal to mass of Jupiter is 320 times that of mass of Earth. So it's 1 over 320. That's the mass of Jupiter that many times larger. And what we have is we're interested in finding out what's the radius of the Jupiter. So that's in terms of the radius. So we immediately have Jupiter over radius of Earth square is 320 divided by 2.4, which means this will be a square root. That's 3200 divided by 24, and we'll take the square root of that. So that's about 11.55, so that's about 12. To 2 digits, that's 12. So radius of Jupiter is 12 times radius of Earth, which gives us the radius of Jupiter as 12 times radius of Earth is 6.4 into 10 raised to 6 meter, which comes out to be 7.7 into 10 raised to 7 meters. Let me pause this for a moment and I'll come back to it in the next problem. Problem 2 in homework 5. Here we have, let's start with part A. We have a surface, that is a mass m sitting on the surface. We identify the forces acting on this mass, that is gravity acting downwards, that's mg. There's normal force acting upward because it's in contact with the surface, and that is all. Like in part A, that is all the forces acting on it, and it's not accelerating. So Newton's law tells us that mass times acceleration, so the acceleration of the mass m is equal to mg as a vector plus the normal force as a vector. Its acceleration is 0, so that's equal to 0. These are all forces acting in the same direction, so we just have to take care of the signs. That's minus mg plus n. This vector, we can write this as minus mgi plus ni, or minus mj and nj, and then we get the same information here. So the normal force is equal to just mg. We given mass m to be 10 kgs, so it's 10 kg times 9.8, so that's 98 newtons. That's a normal force acting on the mass m. In part B, there's a small modification to the problem. Again, we have the same surface, and there is a mass m sitting on it. But now there is an upward force F acting on this. So of course there is mg acting downward. That remains the same because Earth is still, it is in fact sitting on the surface of the Earth. It is still in contact with the surface, so the surface still tries to resist the mass's tendency to fall towards the center of Earth. That's the normal force. In addition, now we have a pulling force, let's call that F. So a force F is pulling the mass up. These are vectors if you want. And we have MA is equal to mg plus normal force. But now there is an additional force of F. So there are three forces acting on the mass m instead of two. The acceleration is still given to be 0, so that's equal to 0. And or instead of given, we should try to understand what would happen if the force was large enough, then it can even lift off. So that's a scenario. But here we are assuming that it is static and acceleration is equal to 0. So then our equations become minus mg plus n. The forces act being pulled upward, so that's plus the force F. So the normal force is equal to mg minus force F, which gives us 0.8 minus 20 newtons. So that's 98 minus 20. So that's equal to 78 newtons. So if you had a weighing scale that was measuring the weight of this object, the weighing scale will measure less weight for the mass, or will measure less mass because it's calibrated to measure mass. Less mass for it because there is a force F that is acting on it. So it pushes on the weighing scale less relative to what it was doing earlier. Let me pause here. This is problem 3 in homework 5, and it talks about an elevator. So that's the elevator, let's say, and we have a mass m sitting on it. What are the forces acting on this mass m? That is mg acting downward, and the floor of the elevator will resist the mass's tendency to reach the center of Earth. So that's the normal force, and the weighing scale measures this normal force. In part A, in general, this could be accelerating. This uh, whole elevator could be accelerating upward, downward, or it could just not be accelerating at all. And those are the questions being addressed um, in the problems. It is at rest. If it is continuously at rest, then the acceleration is equal to zero. So we have mass times acceleration is equal to minus mg plus n. That means 0 is equal to minus mg plus n. That means n is equal to mg. And m is 75 kgs and g is 9.8 meters per second square. And what we have is so it's 735 newtons. In part B, we are told it's moving upward at constant speed. If it's going at constant speed, acceleration is still zero. It doesn't matter whether it is going upward or downward. You still have the same equation. So it's ma is equal to minus mg plus n. So acceleration is zero still. So it's minus mg plus n. So that immediately implies that n would remain the same. So it's 735 newtons. So nothing changes. So notice you're still moving in the elevator, but just movement is not necessarily sufficient. We need to have acceleration. In the third part, we are showing it's slowing down at 2 meters per second while moving upward. So if it is slowing down while moving upward, so the acceleration is equal to minus 2.0 meters per second square in the downward direction. So let me say this j hat, right? So j hat is upward. So we have mass times acceleration is minus mg plus n. So, but it's minus ma. So since it is acting downward, it is minus ma. So the normal force will be mg minus ma. That's 735 minus of 75 times 2, which is 75 into 2 is 150. So 735 minus 150 is 585 newtons. Again, notice it is slightly counterintuitive because typically even if we cross the first stage where we accept that acceleration reduces or increases the mass, but when we are going upward, it is not necessarily always increasing mass. Since we are slowing down, it is effectively accelerating downward, which we say it's decelerating upward. In that sense, it is lighter, and it is lighter by how much? It's about lighter by 150 newtons, which brings down its mass to 555 newtons. We can do similar problems for various other accelerations we can think of, even in a diagonal direction, but we won't address those things here. So let me pause this for a moment. This is problem 4 in homework 5. It talks about a, a student who is skateboarding down a ramp. So the ramp is effectively this shape, and the angle theta is given to be 15 degrees. We have, let's represent the student's mass as a block. So that's your mass M. We identify the forces acting on this. Firstly, that is a gravitational force acting downwards, vertically downwards. Normal force this time is normal to the surface. The surface is not horizontal, so the normal force will be making an angle N with respect to the vertical. What is the angle it makes? If this is angle theta, that's angle theta. That's your two forces. So we start from Newton's second law. So mass times acceleration is equal to mg plus the normal force, written as a vectorial equation. We break this into the x direction and y direction to get the individual algebraic equations. So that's y direction. The x direction, the force equation reads, and we have to, before that we have to choose what is our x and y direction. So that's your y, that's your x. So we say acceleration is purely in the x direction, so it's mass times acceleration is equal to mg has a component of sine theta along the x direction, and normal force has no component in the x direction. In the y direction, acceleration does not have any component in the along the y direction. Mg has minus mg cosine theta, and the normal force is purely in the y direction. So we have the masses cancel out, so acceleration is equal to g sine theta, and the normal force is equal to mg cosine theta. That's your two equations for the system, and from this point we can try to do the numerical problem. But before I proceed, I can say what is the acceleration here. So this is 9.8 times sine of 15, which will be equal to and that's 2.5 meters per second square. Let's do the problems in parts. So part A tells us identify the forces acting on the student, choose the coordinate system so that the acceleration is along one of the axes, and draw a force diagram and identify the uh, uh, forces. So the forces are of course mg acting downward and the normal force acting upward. That's the two forces. Part B, determine the acceleration of the student. We calculated that to be 2.5 meters per second square actually. And in part C, we have to find the speed of the student at the bottom of the ramp. That's a kinematics equation problem. So we have what's the distance the student moves on the ramp, that's given to us to be 6 meters, and it is positive because x is positive as we go down the incline. Time taken we don't know. The initial is actually 3 meters per second. Is not starting from rest. The final we don't know. That's what we are actually interested in calculating. And acceleration due to gravity is 2.5 meters per second square. The equation we would use is the one that is missing delta t in it. So we have the equation v final square is equal to v initial square plus 2 times acceleration times delta x. So v final would be square root of v initial square, that's 3.0 square, plus 2 times 2.5 times 6.0. 6 into 5 is 30. 30 plus 3 square is 9. And we have to take a square root of that. So that's 6.2 meters per second. Let me pause for a moment. Resuming the recording. Let's work on problem 5 in homework 5. Here we talk about 3 masses kept on a horizontal surface. So that's a horizontal surface, and we have 3 masses on it. So that's the second mass and that's the third mass. Let's call them M1, M2, M3. The masses of Q1, and there is a force F acting on from the left. The vector force F. Let's write down the equations for each one of them. Or before that, we should draw the force diagram. So we have M1, that is M2, and M3. They are in contact, but we are identifying them separately. That is, of course, M1G and normal force acting on each one of them. But the relevant quantities are in the horizontal direction, so this is not going to play an important role in the problem. So that's the vertical forces, 3G and M3. To begin with, there is a force F acting horizontally to the right, but it's acting only on M1. Because M1 tries to move to the right because of the action of the force F, M2 tries to resist that. So there is a force, contact force, on 1 due to 2. So that would be C12. This is the force exerted on mass 1 due to mass 2. That's our notation Cij as given in the problem. But due to Newton's third law, M1 will exert an equal and opposite force on M2. So there will be a C21 acting on mass M2. The same thing happens at the interface of M2 and M3. M3 tries to push M2 with C23, and M2 pushes on M3 as per Newton's third law. That's C32. And the magnitude wise, Cij is always equal to Cji. So we can write down the equations now. Let's start with M1. We have M1A horizontal components alone. So that's F minus C12. For M2, we have M2A is equal to C21 minus C23. And M3 is M3A is equal. So there's only one force acting here, so this time, so that's C32. Also, using Newton's third law, we know that magnitude-wise, C12 is equal to C21, and C23 is equal to C32. Based on this, we can begin by adding all three equations. All the contact forces cancel because they come in opposite signs. So we immediately have M1 plus M2 plus M3 times acceleration, that is adding all three acceleration terms on the left, and on the right there is only one force that survives. Right, this C12 cancels C21 and C23 cancels C32. So we immediately have acceleration is equal to the force acting on the left, mass m1 divided by m1 plus m2 plus m3, which in the problem given to us, I think the problem should be giving us a force F. The complete information is not there. So at this point, let's, so typo in the problem, like I should be stressing on this. So there's a typo and problem, typo or correction in problem. So the F should be given to us. So let's say F is given to us to be 150 newtons. Let's make it 180 newtons. That's necessary to proceed because otherwise we cannot find the acceleration. If that is the case, then we can immediately say this is 180 divided by 10 plus 20 plus 30. So that's 60 divided by 180. So and we have 180 divided by 60. So that's 3 meters per second square. Let me see if the problem really requires me to calculate F. So going back to the problem, part A asked me to identify the forces acting on each of the three masses. We already identified them to be M1, it is F and C12, M2, it is C21 and C23, and M3 is C32. So that's the identification of the forces. And part two, using Newton's law, determine the equations of motion for all three masses. So that's your equations of motions. So that corresponds to part B. It doesn't really require us to calculate F. And if Cij are the contact factors acting, determine C1, 2. So that plus the problem is only asking us to calculate C212 in terms of F. So this is really uh, not a typo, and it's not really asking me to calculate uh, this acceleration A, right? So, so this is not necessary. Right? So basically, this equation is correct, but I don't have to really proceed on to calculate the acceleration. In part B, we have to calculate C1, 2. So once we have the acceleration A, I can calculate C1, 2 in part B. So C1, 2 would be equal to F minus of M1A. That's starting from the first equation in the set of three equations there. And that's equal to F minus of M1A, where A itself is F over M1 plus M2 plus M3, which is exactly equal to M1 cancels out when we uh, make the denominators common. So we have M2 plus M3 divided by M1 plus M2 plus M3 times F. Notice that the problem is not really asking me to calculate any numbers. It's just the algebraic equation that it is asking for. I got confused a little bit here. I was expecting it to ask for some numbers, but it's not. So we don't need this. We don't need this. But hopefully I didn't confuse too much. I was just trying to look for numbers. But so the answer to part B is just this. Okay, I'll pause here for a moment. Pause. This is problem 6 in homework 5. This is the Atwood's machine. We also discussed this in the class today. So Atwood's machine consists of a pulley and we have a mass M hanging on one end of the Atwood machine, and there is a mass M2 hanging on the other end. So that's and let's say M2 is heavier than M1. Let's assume M2 just for one of them has to be heavier, otherwise there won't be any motion at all. And let's identify the forces acting on it. That's part A. On M2, there is M2G. It's a force of tension upward, and it will accelerate down with an acceleration A. M1, there is M1G acting downwards. There is a force of tension in the rope because the rope is pulling the mass M in the upward direction. And M1 is going to move upward with acceleration A. The concepts here are that the force of tension are the same in both the wires. That's because we're talking about massless wires. And also, since the wires do not stretch or get compressed, the acceleration A of M2 and M1 are magnitude-wise exactly the same. This lets us write the equations for the two masses. So we have M2, as far as M2 goes, the equation of motion is mass times acceleration. M2 times the acceleration of mass M2 is equal to so it's in the downward direction, so it's minus and we have minus m2g plus t. Or if often you would say m2g, m2a is m2g minus t, that's perfectly fine as far as you realize the signs. M1a, acceleration is going upward, and we still have m1g acting downwards, plus t. Right? You would say this is the difference between the forces, t minus m1g is equal to m1a. That's another way of seeing it. We are interested in solving for t, not the acceleration. What you typically do is that since t is common in the two equations, we can subtract the two equations, one from the other. So that's, you subtract the two equations, t will cancel out. So what we get is minus m2a minus 1a is equal to minus m2g minus of minus m1g. So what we have here is minus m1 plus m2 times a is equal to m1 minus m2 times g, which gives us acceleration a to be equal to m2 minus m1 divided by m2 plus m1, which will always be less than 1 because the ratio of difference between two numbers over sum of the two numbers will always be less than 1. So we know that acceleration of the mass m2 will be, or mass m2 or m1 will be always less than the acceleration due to gravity. But the problem is asking us to calculate the force of tension. So to calculate the force of tension, we go up the first or second equation. So T is equal to m2g minus m2a. So that's the same as m2g minus m2 times, we substitute the acceleration solution into that, and we again simplify this. When we simplify m2 square and m2 square, there's two of them cancel out, and what we have is m1 and 2 comes twice with them, so it is 2 times m1 m2 over m1 plus m2 times g. That's the force of tension, and that's part C. So this will be part C. Part B was using Newton's law to determine the equations of motion. So that's part B here. So that's part B of the problem. And in part A, maybe I should do somewhere here. As far as M1 goes, there is force of tension, and there is M1G. And as far as M2 goes, there is force of tension, and there is M2G. That's the forces acting on that. And it's again an algebraic equation. We don't ask any numerical numbers that leads to the force of tension given when the masses are given to us. Let me pause here. This is problem 7 and homework 5. We have a mass m, and it is above the ground. If it is, a mass is held above the ground, that means it is not in touch with the ground. That's what it is meaning. And There is there are two ropes holding it there, and they're making an angle of 30 degrees and 45 degrees. So let me draw those. So that's one of the ropes, right? And the other rope is making an angle of 45 degrees. Each of these rope will exert a tension T. So let me show that. So this is T1, vector T1, and that's vector T2. That's the forces acting. And there is also mg acting downward. That's your three forces acting on it. I can specify this direction of this vectors more precisely. It is acting at an angle of 30 theta 1 with respect to the x-axis, and the second force is acting at an angle of 45 degrees with respect to the negative x-axis. In part A, we are asked to identify the forces. The forces are, of course, mg, T1, and T2. So three forces acting on it. Using Newton's law, determine the equations of motions for the mass m, part B. So that's m times acceleration A. That's equal to mg plus T1 plus T2. That's Newton's law. That vector sum of the forces acting on the mass m is equal to mass times the acceleration of the mass m. The mass is just held above the ground. That means it is stable up there, so its acceleration a is equal to 0. So the equations might simplify a little. So it's mg plus T1 plus T2, which means that if these are the three forces acting on the mass m, and if the mass m is not accelerating, these three forces have to cancel each other vectorially in an exact form. And that allows us to calculate these forces. So that's the requirement in part C. Let's split this vector equation into x and y direction. So there is an x direction. In the x direction, the left hand side is still 0. mg does not have any x component. T1 has an x component. Since T1 is in the x or second quadrant, it will be minus of T1 times cosine 45. It's cosine because the angle that's given to us is adjacent to the x-axis. T2 x component of T2 will be T2 cosine 30 centimeters. So it's 30. Similarly, we can do this for the y direction. Left hand side is still 0. mg is minus mg, where m is given to us to be 20. And the y components of both T1 and T2 are positive because they're on the first and second quadrant. And both get sine of the angles between them. So it's T1 sine 30 plus T2. Oops, so it's T2 cosine 45. Oops, mistake. That's sine 45. I noticed that I may place the angles wrongly here. So this should be T2, or not the angles, the magnitude of the, that should be T2, and this should be T1. T1 makes an angle sine 30 and T2 makes sine 45. Well, that's all. Fine, these give us two equations. Let me write the two equations down immediately. So we have cosine 45. Substitute the numbers. Can even do this algebraically if we want. So this is 0.71 times T2 is equal to cosine of 30, 0.87 times T1. So I can say T2 would be equal to 1.23 T1. I can use that in the second equation to get mg. First of all is 20 times 9.8, that's 196. So I get 0 is equal to minus 196. Sine of 30 is half exactly, so that's plus 0.50 T1. Sine 45 would be 0.71 T2. So we get 196 coming to the, bringing it to the left hand side. 0.50 T1 plus 0.71 times T2 is 1.23 times T1. That gives us T1 is 4.71 times 1.23 plus 0.5. So that's 1.37. And I need to 196 divided by, and that's 143. So that's 140 newtons as far as two sig digits goes. But we actually, no, because mg is involved, g is there, that's 2 6 digits. So I can report it only 2 6 digits. So answer should have only 2 significant. Once I know T1, I can put it back in the second equation to get T2 is equal to 1.23 times 140. And that gives me 40 times 1.23. And that's 170 newtons. Now that's the tension in the strings. Clearly, the left one has more tension in it than the right one. I'll pause the. This is problem 8 in homework 5. Let me draw an incline, or it's not really an incline. We have, oops, we have a corner of a table if you want in that, in the shape described, and we have a pulley, and there are two masses. The surfaces are massless. That's a rope connected, and that's M2, and that's M1. We have to first identify the forces. There is gravity acting downward on both the masses. This is M2G, and that is M1G, acting here. There is no normal force that acts on M2 because it is not in contact with a surface really. M1 is in contact with the surface, so the surface exerts a normal force N1 perpendicular to the surface. There is a force of tension that acts on M2. It resists its fall, so that's force of tension. And the same force of tension acts on M1 in a horizontal manner. The tension gets transferred to the other end of the string because it's a massless string, and it exerts a force, horizontal force, M1. That's your three. Well, that's your two or three forces acting on M1 and two forces acting on M2. So, going by the problem, identify the forces as far as M1 goes. There are three forces. So it's M1G, it's normal force, and there is a force of tension. And M2, there is only two forces, the gravitational force and the force of tension, which is acting in the upward direction. Write down the equations of motion for when it comes to M1. As far as vertical forces go, we have there is no acceleration, so that's 0 is equal to minus m1g plus n1. The vertical direction, these two forces has to cancel each other because there is no acceleration in the vertical direction. So n1 is equal to m1g. That's one equation we have. The second equation, which is in the horizontal direction, m1 is going to accelerate. So the acceleration of m1 will be exactly the same as the acceleration of m2. So this is going to move. So the amount of movement m2 will have, because it's connected to m1, will be exactly the same as the amount of movement m1 will have. In that sense, they will have the same acceleration. So m1a, the horizontal direction, it's only one contribution as far as force goes. That's m1a is equal to t. That's your second equation. And when it comes to third equation, that's for coming from M3, which is all in the vertical direction. So we have M2A is getting contribution from M2G minus T. If I were to write it as a vector equation and then input the signs, I would say this is minus M2A is equal to minus M2G plus T. But typically, you can look at this diagram and right away intuitively write this equation. That's your three equations. Let me label them. So that's 1, that's 2, and that's 3. That's your three equations of motion. And that's what is asked in part B. Coming to part C, determine the acceleration of the masses. To determine the acceleration of the masses, we use equation 2 and 3. So let me write down using 2 and 3. So let me write them down again. So M1A is equal to tension T, and M2A is equal to M2G minus the force of tension. That allows me to substitute one in the other, or I will just add these two equations, and I get M1 plus M2A is equal to M2G. Force of tension cancels each other, and that immediately gives me the acceleration A to be equal to m2 over m1 plus m2 times g. We have the masses given to us, so we can get this acceleration A as a number. So it is m2 is 2, and it is 1 plus 2 yeah, times 9.8. So that's 2 divided by 2/3 of 9.8, which is 6.5 meters per second square. So we pause the recording.